Hello and welcome. Welcome to this presentation, which was meant to be given at NAB 2020, but I'm giving here as part of the Connected Media and NAB virtual show from my study. The subject of the presentation is video compression, very much one of the reasons why I'm able to kind of record and stream to whatever device you're watching this on, this content. And in particular, one and the latest of the MPEG standards, LCEVC or MPEG-5 Part 2. A paradigm shift in codec standards because it's a standard very different than the standards that preceded them. It's a standard to help other standards in a way. So before we go deeper into LCEVC, and during this presentation I want to explain a little bit how it works, the inner workings of LCEVC, as well as give you data points as to its performance, both computational and from a compression perspective. Two dimensions are very important and very much both constitute the foundation, the rationale, let's say, for the new standard. So we live in a world that it's multi-codec, right? Different codecs, perhaps for different purposes, but certainly a multiplicity of choice, which is great. There's no longer really a size fits all, and video delivery workflows can be fine-tuned to the exact need of an operator. As I said, this is a good thing because a 10–15% savings or the launch of a new service can really, in this competitive market, make the difference for operators. And services like Netflix, services like Amazon, Twitch, already adopt a multi-codec strategy for this very reason. So adopting a multi-codec strategy is not necessarily easy in a way, right? One has to think about, which codec to deploy, where to deploy it, when to deploy it. And I think I like to map the decisions and the considerations that usually take place into three main decision axes: the compression performance of said codec, the running cost of said codec, and the compatibility of the ecosystem. So when I talk about VQ or compression performance, is how much can the deployment of this new codec improve the quality of my service or reduce my delivery cost? As I said, even a small percentage can make a massive difference to the bottom line of some of the services out there today. Running cost or computational performance of the codec, how easy it is to deploy onto my infrastructure or even a public cloud infrastructure. Am I going to pay these services, a lot, or do I need to build a whole new data center to deploy this codec? And the reach and compatibility with the existing ecosystem, how compatible the new service is with the devices where the service is meant to be consumed, right? Is it a browser? Is it a PC? Or is it a mobile phone? Okay, so along these three dimensions, here's like, I'm starting to play a little bit with figures just to give you the idea of kind of like the relative impact of these two dimensions. And I say relative because on purpose, numbers, I haven't put numbers on these slides because when it comes to compression performance, it's really difficult. It's a bloodbath typically when we go into looking how much more performance a given codec gives you compared to a similar codec or a previous generation. It depends on many variables, including operating points, codec implementations, the metrics that are used, the parameters used in encode, the rate control, whether it's used or not used, whether we're doing live encode, whether we're doing file-based transcodes at 1 frame per second. Right, but roughly, and again, taking away all of these dimensions, roughly we know that from generation of codec to generation of codec, every generation we target kind of half in the bit rate required for to give a given quality to a video stream, or say half the file size of that video stream at a given quality. What we often don't remember, don't consider, or kind of overlook, if you want, is that, you know, at this generation, we obtain this increased performance because the number of tools that we deploy in compression and the sophistication of these tools increases also massively. And from a generation to a generation, we see increasing complexity of 8, 10 times, right? To the point that the next generation of video codecs now compress, 30, 40% better than the previous LCEVC, let's say, generation, the current generation, I should say, but have a kind of transcoding computational costs that is order of magnitude larger, which, you know, bears the question, are they going to be feasible in a real life scenario, you know, at costs before, you know, dedicated chipsets maybe find their way into the market? Well, what if there was a way to, an approach, let's say, to impact both of these dimensions? So to improve the quality or the efficiency from a compression perspective of a given codec, but also make it computationally lighter. And this is really the target and the rationale behind LCEVC, so low complexity enhancement video coding. And this was the, you know, like, it's not the exact words, but the call for proposal that came out of MPEG in 2018 requested exactly this: a proposal for a codec agnostic tool to be used into what we represent here often as a base codec. A codec agnostic tool could be an MPEG codec or a non-MPEG codec that improve its performance and brings it up to that of the next generation of codecs, while at the same time maintaining compatibility with the ecosystem of devices out there. So of low enough complexity that it's deployable in software on the ecosystem of devices that are available. So how is it possible? And before we go into the inner workings, I just wanted to kind of like simplify the concept, you know, with a very simple equation. So I use this simple equation to help highlight the concept that LCEVC is complementary to other technologies, not a substitute, and allows to get more out of an existing codec, let's say C in this case. So the scaling factor of LCEVC is applied to reduce the complexity of C, an existing codec of any kind. And, you know, this is what LCEVC, we will see, does when it performs a reduction of the size of this base codec to a half, a quarter, or a smaller resolution than its final display picture. Then he adds an enhancement. So he encodes kind of like the difference using a light and efficient mechanism, right, which we will go into, efficient in terms of computational complexity, so that the kind of lower complexity C plus this enhancement data is overall lower complexity than encoding the full picture with C. And this is exactly what LCEVC does. And this is how it does it. So you take a input image, it could be a UHD image, an HD image, an image of any size, and provides the base codec, you know, a reduced version of the image in terms of size, a downsampled version of the image. And then it encodes a dual layer of residual data, one at the lower resolution and one at the higher resolution. All this information is packaged together for delivery. And at the decoding end, the process is applied in the opposite order. So the video stream with the base data, let's say AVC, HEVC, AV1, is decoded by the standard decoder that is available on the device already. typically on the on the hardware chipset kind of shipped with the device. And then the enhancement is decoded in software in parallel, and the two elements, the two decoded streams, are combined to give you the enhanced image at full resolution. So this is how the process works, how the process looks, if you want. This is what these kind of like encoded residual data looks like. So if we take away, if we downsample an initial image and re-upsample it, this is what we would see at that top layer as the difference between the two images. And this is what LCEVC and the tools available in the LCEVC is very efficient at encoding. So you can see here, as I highlighted on the slide as well, this is sparse, highly detailed information that is impossible to infer with an upsampler without the original information, but it's also difficult to encode effectively with kind of standard tools and transforms. So there's a lot of high frequency content in this image, which in the DCT space, sorry, transfers typically used by generations of MPEG coding are more difficult to encode effectively. So LCEVC uses different tools, different transfers to encode this information effectively, transmitted alongside the kind of base encoder stream, and reconstruct the image at the decoding end. Again, a couple of examples of how this looks. So on the left-hand side here, you have an image that is just being upsampled, let's say, and on the right-hand side, an image where the the coded residual information has been added. So if you look at the checkerboard on the notebook here, it's quite evident, having zoomed in, that that information was not retained by just downsampling and upsampling, whether that information was transmitted using LCEVC, the enhancement layer. Other things very evident, if you look at the 34 miles an hour or the date on the display or the writing on the advertising billboard, it is quite clear how the residual information kind of carries valuable, high detailed information that is kind of visibly making an impact. Again, this is how LCEVC works a little bit more in detail. So as I said, there's a decoded base picture to which a first layer of enhancement is added, typically used to correct artifacts in the base encoding process. The image is then upsampled, and more information, the very sparse, detailed information that I showed you, is added at full resolution to show you the full resolution picture. Again, more than words, images, and I will show a couple of screenshots here during the presentation, is the impact it has. This is a screenshot from a live stream encoded on one side with X264, on the other side with X264 as a very popular implementation of AVCH264, but where the enhancement layer LCEVC has been applied. So again, here you can see the writing on the stadium, the texture on the grass, the details on the right-hand side are much more pronounced. And this is because the enhancement layer carried that information. This is a live CBR example at 1.4 megabits per second for those of you who are interested about the operating point. So again, another example, and here we're talking about, this is two different bit rates, because what I wanted to explain and to highlight is the fact that yes, we add enhancement information, and we add with this layer LCEVC adds detail at the highest resolution, but with all compression mechanisms, how we leverage that better efficiency may vary depending on the application. So on one side, we may decide to get the better video quality, the best video quality for our service. On the other side, we may want to leverage the compression for bitrate savings and bandwidth savings. So in this case, we'll show you a mixture of both, where the picture on the right-hand side uses less data, like about 60% less data, and yet maintain, if you see the texture on the court or the rail bar at the top, you know, just much more detailed than on the left-hand side, where we use that 2 megabits per second AVC in its X264 implementation on its own. Okay, and all of this, again, you know, I'm not going to go into each of the different tools, but I just wanted to highlight in these slides that LCEVC does this with low complexity. So there are plenty of tools. I think VVC has more than 100 tools in its arsenal, in its portfolio. With LCEVC, we are in tens, right? Less than 10 tools that are familiar with codec experts, you know, entropy encoding, quantization, transforms. There's just applied differently and different transforms that ensure that that residual data can encode it as efficiently as possible. So I'll show you a few screenshots, but you know, a lot of people can process a large amount of content and rely on different metrics to ensure that the content meets the quality expectations as well as visual quality. I personally, you know, will always support the visual inspection of a clip, and I will show you as well why in a couple of slides. But you know, when you go through the process of analyzing hundreds and hundreds and thousands of different video clips at different operating points, the metrics are often necessary. They are necessary. And so the LCEVC has been put through the paces within MPEG and without MPEG, and I'll show you here a few of the numbers where we show exactly the results of some of those tests. So in this case, and again, I'll get a little bit technical perhaps, but LTM that you see on top of the slide there is the LCEVC test model. This is the version 3 from January of 2020. So there is a version 4 that is being released now in May as LCEVC achieved DIS, or Draft International Standards status, and is entering the ballot. So an LTM version 4 with additional improvement is being released. And these are some of the results from the common test condition, the test conditions that are set by MPEG and cross-checked and validated within different members of MPEG, which have gone through this exercise with LCEVC. Again, here I chose, out of the full set of clips that are available, I chose 4, I think. You see there, Food Market, Park Running, Campfire, and Fortnite. I chose 4 to give you an example. You'll see at the bottom kind of the average across all of the clips. But I chose them just to highlight how different metrics will give you different values. If you see the average for the Class A, at the call for proposal was, you know, -8% almost in savings if you were to believe PSNR, -24 if you were to believe VMAF, and almost -50% if you were to believe mean opinion score. So this subjective evaluation of the clip. So even kind of more strongly, if you see Fortnite, will give you a PSNR that is +8%, but at the same time a VMAF score that is -10%. So again, visual inspection in these cases will be necessary. But for fairness, across all the different numbers that I will show you, I'm not going to go into detail on each and every one of them, but I chose to use all 3 metrics to make sure that I presented the results as fairly as possible. So here is an example again of the test model 3 across different clips. And as you can see, whether you go from PSNR to VMAF to MOS, so mean opinion score, subjective evaluation, LCEVC performs an LCEVC enhanced HEVC stream, which was produced by HN, so the test model of HEVC produces better results than HN, so the HEVC implementation by itself across all of these different clips. And so those clips were, those figures that I showed you were for ultra high definition. Similar story for high definition. In this case, we're mixing both H.264 or AVC and HEVC or H.265 with their enhanced version. So in this case, for example, you will see that you can go from in 264, so here, to a version that is enhanced. So either, you know, these curves, these BD rate curves can be read kind of vertically, an enhanced quality at the same bit rate, or a massive, let's say here, reduction in bit rate for a given quality. And the same for HEVC or X265, in this case as an implementation of HEVC, going from here to a higher quality picture or to a large saving in bit rate. And again, 2 clips, in this case, looking at VMAF scores. And again, we've done a lot of these tests, not as only as V-Nova, but as I said, the tests have been cross-checked within MPEG. This is again a result across a large set of clips that are available online from Netflix, the L-Fuente test set, 136 video sequences, where we compared X265, very slow as a preset, is the preset of X265, versus the same implementation, so X265, but LCEVC enhanced. And as you can see here, the collective output is shown in 2 different bar charts, one using VMAF, one using PSNR. So if you were to believe VMAF, pretty much an enhanced version of X265 will produce a better quality stream, and it's 61% of the time with PSNR. If you look at the median rate across all of these different clips, again, VMAF tells us that enhancing an X265 stream will give you a 30% better bit rate for your clips. If you look at PSNR, would be an almost 10%. So again, this just to show you the sheer number of different tests that are being put through, that LCEVC has been put through in order to kind of like validate and understand how well LCEVC can enhance the performance of an existing codec. As I said here, I showed you examples with H.264 and HEVC, but we have data for other codecs as well. Let's not forget, though, that we said, you know, this is a low complexity enhancement. So it's great that it provides an increased performance from a compression perspective, but let's not forget that the call for proposal asked us as well to create a standard that could be applied to any codec, but without increasing its complexity. So that could be deployable, whether it's encoding or decoding, on existing devices. And again, here I can take a couple of data points, looking at, again, X265 in the encoding, on the encoding side of things, so on the left-hand side of your screen, where we show that different presets will have kind of generally different behavior, but similarly, their complexity are reduced by almost a factor of 3 in the case of a very slow preset. And this is why the very slow preset is applied to a smaller resolution picture. On the decoding side, similar story. Here using LibAV, an open source version of HEVC for decode. Again, the complexity or the speed of decode is increased by a factor of 1.5. Again, demonstrating that the combined LCEVC and HEVC stream it's lighter to encode and to decode than the native format at the same resolution. Okay, those were some of the numbers, especially the one in MPEG, that are created without rate control in certain test conditions, and they're used mostly to evaluate the performance and the worth of certain tools that are added to the standard. But what about real live and linear kind of constant bitrate scenarios, when things get even more complicated, and complicated because the quality of the picture doesn't stay constant throughout the length of the stream or the program, right? It varies. There are scenes that are more difficult, scenes that are easier to encode. And so it is interesting also to start understanding how the enhanced stream behaves when the quality of the stream varies. And here, I think we're pushing the native encoder to its limit. I think in this case, it was H.264. But just to show you that going from left to right, again, here I'm using yet another video quality metric, MSSIM, but the behavior is similar with VMA for PSNR. And you see this constant kind of like troughs, this constant collapse of the video sequence, where in places like this, the image, that part of the sequence is particularly complex, and the net result is that we'll see the very common and unfortunately known artifacts of block-based codecs. In this case, it's literally blocking, but banding and other visually impairing artifacts will happen in those situations. Again, with an LCEVC enhanced stream, what we see is that generally, even when the quality is better and when things are easier, great, we will get that amount of extra details that I showed you before and I talked about. But more importantly, when things get really bad, see, the streams is more resilient. Okay, and therefore, from a subjective perspective, from a customer's perspective, looking at the video stream, the LCEVC enhanced stream will be a lot more pleasant because it will never collapse in those blocky artifacts. For example, they're typically seen in with block-based codecs. And again, and this goes some way to explain why the MOS scores were so much higher, if you want, because on average, it's a metric will give you the average across the whole length of the clip, where subjectively the user, your users, are very sensitive to the areas where the picture is either particularly sharp or particularly well detailed and the details are maintained, or conversely when the picture doesn't deteriorate in a way that makes the service unpleasant to watch. In a way, again, more and more curves, right, across 264, 265, in this case, in real life conditions. I'm not going through all of the pictures, but this is just to show you, and these results are available. I don't know if anybody wants to contact us to, and they're replicable across these clips, which are also available to download. But again, here what I wanted to show is that across all of the different clips, and in this case with movies and animation in real life, linear kind of CBR streaming scenarios, LCEVC improves the performance of X.264 and X.265, while at the same time, remember, improving the computational performance as well. Same against sports, esports. In this case, we're talking 1080 high frame rate content, P60. Again, across all of these different clips, LCEVC provides a performance improvement, and this is using different type of metrics. But visually, as I said, subjective evaluation further supports this argument. And I know that I'm going through a video compression stage, and you're probably going to go through another video compression stage before this video is being streamed to you. But what I want to do is kind of like show you visually what I mean by this. So if you see, in this case, you have X.264 at the top at 3 and 4 megabits a second. So fairly standard kind of like operating points for streaming. And at the bottom, you have again 3 and 4 megabits per second for the enhanced version of that same codec implementation. And so you can see in the kind of like the texture on the grass or the texture on the tarmac or the kind of like artifacts on the road are all improved by the use of LCEVC. So in particular, what you see on top of the number 58, there is no present any longer in the LCEVC stream. Again, if we start pushing things even more, when we have constrained bit rate, here we're pushing HD to 1 megabit per second. This is a 30 frames per second clip. But again, on the right-hand side with LCEVC, the details of the numbers on the back of the player or the numbers of the score are much more well maintained. And even more obvious if we really push things down, this is a 480p stream, 170 kilobits per second. So we're really pushing, but in mobile communication, video conferencing, mobile streaming, these are operating points that are more than typical, in congested areas, remote areas. I say congested areas because often that's where the biggest issues arise in mobile kind of delivery. Again, the impact of enhancing the original stream with LCEVC is more than obvious. So to conclude the presentation, so I just wanted to, to remind ourselves, and I think using the words of Jan Ozer in a Stream Media article just recently, we say that LCEVC is a low complexity enhanced video coding, and it's the really only new standard deployable in 2020 this year. How come? How can we deploy LCEVC? It's just got to draft international standard, yes, but there are early implementations of it. So there are libraries already available for Windows, for Linux, for x86 systems, for ARM-based systems, for GPUs, for FPGAs. What I said is from the very beginning, the LCEVC toolset is deployable on existing hardware, whether it's on encoding, and we can demonstrate that today by literally having an FFmpeg version that supports LCEVC, and we can run it on any of these platforms. We have a version in the cloud for people to try it, and there are commercial encoders coming soon that supports LCEVC. Same thing in the decoding. Even more importantly, there are libraries already available for LCEVC on Windows, on iOS, on Android, and even scripted in JavaScript, WebGL, WebAssembly for utilization within a player in an HTML5 compatible browser. And again, here there are plenty of reference integrations or reference application, whether it's ExoPlayer on Android, a VLC kit or an extension to the VTDS within iOS, video.js, HLS.js, Shaka player, all have reference implementation of LCEVC available from V-Nova, and commercial players and various OSs are also coming soon. So as a reminder, just to finish, why MPEG-5 LCEVC? Well, it's why video compression, or why better video compression. It's it improves the quality of the service. It's making the service delivery more affordable, more economical, and reduces the operating cost of firing up yet another video transcoding workflow. And these are very tangible. I hope I showed you some numbers that we can get through higher qualities and higher resolutions. We have examples of deployments where we increase the throughput of a given data center or video transcoding setup by up to 4. Lower bandwidth will increase the reach of your service, reduce buffering incidents, and that reduces churn in return. It's already supported by many of the devices, and not to forget cost. It's the bottom line is important. It reduces the cost of service delivery as well. So You can try yourself. You can contact us. You can contact us to trial and test LCEVC, and there is already a compatible app on Google Play for those who want to give it a try as well. So with this, I would like to thank you. I would like to thank you very much for well, taking the time to listen to my presentation and to join me kind of virtually at this NAB 2020 Content Everywhere presentation. Again, thank you very much. Stay safe, and hopefully I'll see you very soon.